Lecture 1.3, Exponential Functions. This photo is Acadia National Park in Maine. The morning sunrise hits the United States first at the top of Cadillac Mountain in Acadia National Park. The park is the oldest national park east of the Mississippi River. Although some of today's lecture is from the book, some of it is not. I used to tell students that they must take notes to be successful in calculus. However, since you're watching this on a video, you do have the option of stopping and pausing whenever you need to, and taking notes later. Many of the students in the class will be using the TI-89 calculator. You may use either the TI-89 Titanium or the older TI-89. The pictures in the lectures will usually illustrate the older TI-89, although the buttons on the Titanium edition are different shapes and colors. They are in the same positions and have most of the same functions. The TI-89 is an awesome calculator and does amazing things. If $100 is invested for 4 years at 5.5% interest compounded annually, the ending amount is 100 times 1.055 to the fourth, or $123.88. On the TI-89, we'd enter 100 times 1.055 raised to the fourth power and press enter. At the end of each year, interest is paid back in the amount in the account and added back into the account, so the amount of interest gets larger each year. This is an example of an exponential function. F of x equals a to the x. In this case, the x is the exponent, and the a is called the base. Graph y equals a to the x for a equals 2, 3, and 5 in a -5 to 5 by -2 to 5 window. We press Mode, Graph, Function, and we change the display digits to float 6 if it's not already, and the angle to radians. We press Enter. Then diamond y equals, and we enter y1x equals 2 to the x, y2x equals 3 to the x, y3x equals 5 to the x. And you may be wondering why I ask you to change the angle measure to radians, even though this is not a trig problem. In calculus, we set the angle to radians and leave it there because degrees usually don't work in calculus. Then we press diamond window, and we set the viewing window. So we're going to set x min to -5, x max to 5. We set the scale to 1 for the x-axis, y min to -2, y max to 5. We set the scale to 1 for the y-axis, and we leave the resolution 1. Actually, in the titanium models, you don't have the option to change the resolution. Then press diamond graph, and there are our graphs. First equation, second equation, third equation. We can use this graph to answer some questions. For example, where is 2 to the x less than 3 to the x less than 5 to the x? And looking at the graph, we can see it's in this part of the graph. So our answer is x is in the interval from 0 to infinity. Notice that was an open interval because we don't count the 0. Where is 2 to the x greater than 3 to the x greater than 5 to the x? And we see it's in this part of the graph where x is negative. So our interval, x equals -infinity to 0. Once again, we have an open interval on both sides. And finally, Where is 2 to the x equal to 3 to the x equal to 5 to the x? It's where the graphs cross at x equals 0. What is the domain? Remember, domain is what the x's could be. Looks like x could be anything, so we have negative infinity to infinity. What is the range? Which is a way of saying what are the possible values for y. Looking at the graph, y could be any number greater than 0. So our interval is from 0 to infinity, and it's an open interval because we don't count the 0. Population growth can often be modeled with an exponential function. Here's a table of world populations from 1986 to 1991. Now, we find the ratio from each year over the previous year. 523 divided by 4,936 is about 1.0176. And we do that for each pair of years. And we see that for the most part, the numbers are pretty consistent. We have one outlier, but the world population in any year is about 1.018 times the previous year. So in 2010, the population should have been, according to this model, 5,422 times 1.018 to the 19th, because it's 19 years past 1991. Or about 7,609.7 million people. Now you'll have to check that on Google or something to find out how close that estimate was. But it's about 7.6 billion people in 2010. When I first started teaching calculus, this seemed way in the future. Radioactive decay can also be modeled with an exponential function. Suppose you start with 5 grams of a radioactive substance that has a half-life of 20 days. When will there be only 1 gram left? Well, we know that after 20 days, half of the substance will have changed form. So we have 5 times 1/2, or 5 halves left. After 40 days, that is 20 more days, the amount left will be cut in half again. So we have 5 times 1/2 squared, or 5/4. After t days, the amount left is 5 times 1/2 to the t over 20. In pre-calc, you solve this using logs. Today, we're going to solve it graphically, just for practice. So we set our equations. y1 equals 1, and y2 equals 5 times 1/2 raised to the x over 20. And we can set our viewing window. Let's let x go from 0 to 60, because we think our answer is going to be within 60 days. X scale is 5. That means there'll be a tick mark every 5 units on the x-axis. Y min is 0. Y max is 5. That's our 5 grams that we started with. Y scale is 1. And of course, the resolution stays 1. Then we press diamond graph. And when we look at our graph, we can see where the amount present crosses the line that represents 1 gram. We just have to figure out where that intersection is. So we'll press F5, which is math. That's in the menu at the top of the screen. Then intersection, which is 5. We use the arrow keys to select a first curve, a second curve, a lower bound, and an upper bound, and press enter each time. Now we have to select a first curve and a second curve because sometimes we'll be using more than two curves. And we select an upper bound and a lower bound because sometimes the graphs will cross more than once in some problems. So we have to tell the calculator where to look, which intersection we want. In this case, the intersection occurs at 46.4386. That's the x value, or about 46 days. Many real-life phenomena can be modeled by an exponential function with base e, where e is approximately 2.7182818828. E can be approximated by f of x equals 1 plus 1 over x raised to the x power. As x approaches infinity, f of x will approach e. So let's graph this. If we graph the equation using the techniques we learned earlier, this is what the graph will look like. Then we can use trace to investigate the function. Trace is F3 in the top menu. And we see by the time we get to the right-hand side of the screen over here, we're still not too close to E. So we need to go further to the right. We can have the calculator construct a table to investigate how this function behaves as x gets much larger. So we press Diamond Table Set. We set Table Start at 1000. Press Enter. Scroll down. Delta Table equals 1000. Press Enter. Press Enter again. And then press Diamond Table. And the calculator calculates a y value every 1,000 units on the x-axis. And we see as we go quite a ways to the right, 1,000 units to the right, we get 4 digits of accuracy. We could move to the y column and scroll down to watch the y value approach E.